Hi everyone, my name is James, and in this video we are going to be solving the following problem. Consider a system with the following dynamics. So we have a term here, x of t, which changes with time, and we're saying its first derivative changes proportional to the negative of itself plus some control input u, which we haven't defined yet. And in this case, we are going to choose in order to make x behave in a particular way that we choose. And this is really the essence of control theory. As we go through these problems, we are going to develop and learn new ways of creating and solving for these u-terms in order to get systems with not only first order but higher order dynamics to behave in the way we want, and we shape their behavior. And so we're going to break this down into three parts, this problem. The first part is asking us what we would choose our u-term to be in order to ensure that x ends up at 1, the constant 1, as time approaches infinity. So that is to say we need to choose some u in order to make sure that the steady state value of x ends up at 1. The second part of the problem says if x starts initially at 0, so at time 0 the value of x is 0, and we use the value of u that we found that makes the steady state value equal to 1, then we need to sketch the behavior of this system or its dynamics in order to actually see how it changes over time. And I mean, being a first order system here, and if it starts at 0 and it ends at 1, we would expect an exponential rise or a logarithmic looking curve. That's just the intuition, but we'll show that explicitly. And the third part of the problem is asking us how long it will take for x to be within 2% of its final value. So how long in seconds will it take for x to be at 0.98 if it's approaching 1? All right, let's get started. Okay, so for the first part, we have to figure out what u to choose in order to make x end up at 1 as its steady state value. Now, there's a number of ways we can approach this. The simplest way is to use our intuition about the problem. Now, when we say x is at the steady state, so this is as time goes to infinite, we assume that all of the dynamics of the system, so if it was, say, for instance, a second order system, it might have had oscillations, we're assuming they've all died out and the system is setting at some constant value. So if the temperature was changing, it's now at room temperature or something like that, as we've seen before. So with that in mind, that means that the derivative must be 0 because this is no longer changing. So we could assume, if we were going for the steady state value, let's assume that x dot is equal to 0, and we know we want our x to end up at 1 in this steady state. So then x is equal to 1. And if we were to substitute these into this equation, we would get 0 is equal to minus 1 plus u, and the only way this can be true is if u is equal to 1. So this implies that u is equal to 1. Now, this is one way to solve for the u we need in order to get our steady state value to be 1, and it relies on our intuition. If you would rather, we can actually just brute force out the algebra. So as we've seen before, this is a first order system, so we can assume that the solution has a form that looks like this: e to the minus kt plus b, where k here would be our rate of decay and a and b are currently unknown constants. So using what we're given about the problem, we know that as t approaches infinity, so t of infinity, an exponential at minus infinity in this case, this is all going to go to 0, which means we're left with b, and we know that this is equal to 1, so b is equal to 1 in this case. And we've got our xt term. We could start substituting back into here, but we need our x dot term, so we'll take the derivative of this. So we say our x dot is equal to minus k a e to the minus kt, and the b is a constant, so it goes to 0, and we'll just substitute back into our original equation. So we'll substitute in the x dot term that we just solved for is equal to minus, in brackets, a to the e minus kt plus b plus u. So we can pull, let's pull this term here over to the left. So we would have positive a e to the minus kt minus ka e to the minus kt is equal to negative b, and we know that b is equal to 1, plus u. And if we collect terms here, we'll pull the a out the front, which gives us 1 minus k, and the exponential term we'll pull out the back, is equal to u minus 1. And again, we're going for the steady state value of the system. So we know as t approaches infinite, this left-hand side has to equal 0. And so we're left in the same situation we were before, where the only way this can be true is if u is equal to 1. So using our intuition, obviously we can get the answer a lot quicker, but maybe just solving everything out like this might be better for you if this intuition didn't make sense. And it might also be a good idea as we reach higher order systems. I mean, the assumptions still apply, but it's always good to sort of see explicitly how these assumptions work if they're a little bit confusing. And that's part 1. Let's move on to part 2. Part 2 of this problem says that if x is initially 0, so x at time 0 is equal to 0, and u is the value we just found in part 1, so u is equal to 1, sketch the way x changes over time. Well, x is an exponential because it's a first order equation. So we can draw a graph of this, and we know it starts here, and if this is 1, then it must rise like this. So until we solve for k, we don't actually know the steepness of this curve, but that's pretty straightforward to figure out. I'll just rewrite the equation that we just had up. So we had just substituted back into the original equation and ended up with this. And now we can try and figure out what k is, since we need that value. Well, we know what u is equal to. So this right-hand side must be equal to 0 because u is equal to 1. And if we consider at time equals 0, where this exponential term is equal to 1, then we end up getting a by 1 minus k on the left here, which is equal to, we get a and k, and then k is equal to 1, which means based on the form we had previously, we said that x of t is equal to a e to the minus kt, where k is equal to 1, so just t, plus 1, where 1 was our b term, which we solved for as well. And now we can use the additional information we have up here and say that x of 0, which means this is 0, so a plus 1 is equal to 0. We know that a is equal to minus 1. And that's actually all of the dynamics of this system here. So x of t is minus to the minus t plus 1, or if we rearrange that so it's a little bit nicer, this is the equation we end up with. Now for a quick sanity check, if t is equal to 0, then this exponential is equal to 1. 1 minus 1 is 0, which is what we expect. And as t goes off to infinity, this term decays down to 0, and we're left with 1. Bing! This looks pretty good. So this is actually enough information for us to move straight on to part 3. Now, this is sufficient for a curve, especially if you have this additional information, but an alternative is to use MATLAB in order to plot this, and we'll put out a separate video that shows you how to do that. So let's move on to the third part. In the final part of this problem, we just want to figure out how long it takes for x to be within 2% of its final value. Well, if its final value is 1, then we would like to know for what value of t, x is equal to 0.98. Well, we can actually just substitute that in back up here into our equation for x. So when x of t is equal to 0.98, 1 minus e to the minus t. So we subtract the 1 over here, which would give us minus 0.02 is equal to minus e to the minus t. So we'll just get rid of the negatives. And then we can take the natural log of both sides to solve for t, which will give us t is equal to 3.91, I believe, seconds. Actually, I might just show that explicitly in case you're a little bit rusty on that. So taking the natural log, let's cut across to here, we would have ln e to the minus t is equal to ln 0.02, which would be just minus t, because these two things essentially cancel each other out, is equal to minus 3.912. So t is equal to 3.912, which is our 3.91 seconds. And there we go. Figuring out this, calculator, your best friend. And that's the full solution to the problem. Thanks very much for watching.